Welcome to this channel, Dr.ARM's Chemistry. Last time we have seen the coordination number 4 and 5, and today we will discuss the geometry of coordination complexes with coordination number 6. So this geometry of coordination number 6 is very common. It is the coordination number is also very common, and the structure commonly observed for this type of coordination is octahedral. Octahedral. There are other structures also, but they are less common. This geometry is also supported by various experimental observations. Further, the VSEPR approach also shows that this geometry is specially observed for those metal ions where the ligand electrons ligands are easily accommodated around the metal ion and the metal d electrons are ignored. So these complexes can show, the metal ions in the complexes can show higher coordination number, like this coordination number 6. The shape of these complexes is commonly observed is octahedron, but in addition to this, the shapes are prismatic and antiprismatic. In addition to this, the complexes of octahedral geometry are having some distortion, means they are either compressed along the z-axis or they are elongated along the z-axis in the octahedral structures. The common examples observed in this case are ranging for configuration from D0 to D10. So most of the transition elements gives this geometry. We can use some simple examples, that is CO, EL3, 3 plus, then CO, NO2, 3, NO2, 6, 3 minus. So these are some examples, few examples, but there are large number of other examples are also seen. Now, if we see the structure of the complexes of this octahedral nature, we found that the structure is elongated along the axis, like this. It is like this. Means the ligands are showing that these are elongated in this direction. Whereas in some cases the octahedron is compressed in the direction of z-axis. So we can say this is elongated octahedron, and this is compressed octahedron. This is compressed octahedron. So we can have other structures also in which we can find the different examples. these are two more structures. This is trigonal prism, and this is trigonal antiprism. Trigonal antiprism. Now we will see some examples of these structures. So we can have the example of chromium CrF2. Here we observe that this shows the coordination number to be 2, but it is having the octahedron structure. Here the four bonds have 200 pm. These four bonds have 400 picometer distance, and two bonds have 243 pm. So this gives the elongated structure examples. Now we can have the examples of this structure which are having D0 and D1 configuration. For example, Ta, tantalum, Ma6 minus, then Ma6 2 minus, then this has some examples. D0 configuration, it has MO, Ma6, then tungsten W, Ma6, then NB, Ma6 minus, and Ta, PH6 minus. So these are some examples of these various structures. Now we will see the complexes which are having different structures. Now here the D4 and D9 complexes. These complexes are exhibited by D4 and D9 metal ions. But it's elongated or compressed. Now we will see the regular octahedral structures which are having, whereas low spin complexes have less number of coordination, electrons, unpaired electrons. So we will see the examples of regular octahedral complexes. Regular octahedral complexes with high spin nature. High spin nature. Where we have the examples like this. It's a D0 configuration. We have TI-F6, TI-F6, 2 minus. Then with D1 configuration, we have TI-H2O6, 3 plus. Then with D2 configuration, example is vanadium H2O6, 3 plus. Then D3 configuration, Cr H2O6, 3 plus. Then with D5 configuration, the example is Fe H2O6, 3 plus. Then with D6 we show D4 is missing here. D4 configuration is Mn H2O6, MnH2O6, 3 plus. Then D6 configuration FH2O6, PH2O6, 2 plus. Then with the D7 configuration, we have CO H2O6, 2 plus. D8 configuration has example Ni H2O6, 2 plus. D9 configuration has Cu NO2 4 minus. And with the D10 configuration, we have H2O6, 2 plus. So these are the examples of high speed complexes. Now we will see some examples with low speed complexes. Octahedral complexes with low spin nature. For example, with D4 configuration, MnCn6, 3 minus. With the D5 configuration, FeCn6, 3 minus. Then with D6 configuration, CO Cn6, 3 minus. So these are examples of low spin complexes having octahedral structure. So these trigonal, prismatic and antiprismatic complexes, as we have seen earlier, have only sigma donor ligands. There are no pi donor ligands. The effect that is observed on antiprismatic and prismatic structures is because of crystal packing forces, so which makes the difference. Again, the difference between the various prismatic, antiprismatic or prismatic structures in solid state and octahedral state, the structures are changing because of the very small difference in their energy. So if we observe the energy of the trigonal prismatic structures minus energy of octahedral structures, the difference is very small. So the distortion is easily observed due to the bulkiness of these groups. So when the groups are like say phenyl groups, methyl groups are present as ligands. So because of the steric effects, the structure is distorted from octahedral to prismatic. Means the trigonal prismatic or trigonal antiprismatic structures are observed. So with this we will stop our discussion. So thank you for watching this video. Please subscribe to this channel and press like button and bell icon. Thank you very much.